We will discuss some AI research from mathematical standpoint. If you have like data bytes tokens, how do you find structure in those bytes, in those tokens, and how do you figure out what to train the AI on? You see here we have some data points and we grow circles around those data points. And when they grow enough, where they start overlapping, we're gonna connect these data points and look for structures in these connections. I'm gonna let my friend Mohammed speak about this. He studies mathematics and this persistent homology kind of stuff.
So given a spatial set of data, what we're doing is we're assigning structure to it, right? So if we look at it visually, this clearly looks like a donut or a
Okay.
torus,
Okay.
more formally, right? So we want a formal way of actually giving this that structure, and that's what persistent homology does. Okay. Now, the sort of workaround that we have to figure out is that our given data is, sequential. Like we have tokens, right?
Okay.
So this is some number. This is also some number. This is some number. These don't have an obvious spatial structure. So we have to somehow find a way to translate this into this kind of structure before we apply persistent homology.
Okay. Okay. So
The
we
reason why
we have
persistent
some okay
homology,
we have some tokens here, and we want to somehow
yeah.
transform into this donut. But what do you mean by donut structure here?
So a donut structure over here, what we're doing is more formally, it's a torus structure.
Okay.
So, or it's basically a two-dimensional surface called a manifold with a hole over here. Or more formally, you would say that the genus of this surface is called one. So it has some nice properties. Like in math, we look at things like smoothness, right?
Okay.
We look at things like local. We want to make sure it's locally Euclidean. So things like that. These are like properties we look at. This is a donut structure, all right? And you can generally define any more other structures like this, like you can say in layman terms, an eight figure, or this is just a genus 2 tori. Genus 2 torus. So here we have two holes, hence the genus is 2. So genus is just the word for holes.
Okay.
Okay. The thing is, this is 3D space, right? So it's very easy to visualize. When we go to the higher space, then we go from like a loop is a two-dimensional hole. A cavity is a three-dimensional hole. So as you go up in n dimensions, you have, what do you say, different notions of holes. So these all holes collectively are called genus.
Okay.
All
Okay.
right, so that's the notion.
So 2D space we have 2D call a hole, and then 3D space we have like a ball, and inside is a hole.
Yeah.
Okay.
So like if you do a hollow sphere, then it has a 3D hole. Yeah.
Okay.
So like that. Um, so the reason why persistent homology is very like useful is because suppose you have like so from what I've written here, they use this in 3D scanners, right? And that's all I really cared about, and that makes sense. Like if you have, say, for example, if you've been to a dentist, they have these like pen things that they stick in your mouth with a little thing over here, and they make a model of your teeth, right?
Yeah.
So this is kind of what it's doing, right? It's taking in all these individual points, and whichever ones are actually close to each other, it's connecting. Meanwhile, keeping the further points still disjoint. So that's like just one, what do you say? That's like a visual example of why we don't worry about making our data structural in normal persistent homology. Because we have we have spatial data already. the data already comes to us in this form. So the only thing is we need to figure out how many holes it has. All right.
So when you say how many holes, you mean like as we are expanding like circles around the data points? You mean like
Yes.
and
Yeah. So
okay,
the yeah, I'll just
if we like have a sequence of bytes or some data points, whatever. Just want to explain this on YouTube for YouTube. So we have some data points
mm,
in a coordinate system,
yeah.
and we start growing or circles around those data points, and we want to see when those circles connect. So when those circles connect of different data points, then we two
Mm.
components merge into one component. And
Yeah. So I'll just go ahead and draw those then.
okay,
Yeah. So what we're doing is let's take red for the expanding circle.
okay,
Yeah. If we take a circle of epsilon radius around each ball,
okay,
some of these balls are going to connect
yeah,
and some of them won't. So what persistent homology is going to do, it's going to look at whichever ones have like some overlap between their circles,
yeah,
like these two, and it's going to connect them. Now notice how these two circles are individually not connected, so they will not form any line between them. Yeah.
okay, yeah,
Okay. And similarly, now we're just going to keep expanding our circle. And as we expand our circle, this gets more and more connected.
yeah,
Now, the issue with this is obviously the more you expand, the more everything gets connected. So at some point, everything is going to be connected to everything else, right? So it's going to be a huge mess of connections everywhere.
yeah,
But in persistently, so what we're doing is we're varying, say this is like, say epsilon starts from 0 to, let's say, 1 only for now. So we're going to vary epsilon somewhere on this line to the perfect length where we get our data completely structured rather than a complete, what do you say, interconnected mess.
okay.
So this is epsilon equals 0.
How do you know
This
it's
is
structured?
epsilon really greater than 0. Yes?
How do you know it's structured?
Yeah, so that's what we're going to find out. So we want to find a way to detect this hole. Yeah. We are given like our data is given spatial things, so we have nothing else to do but to look for structure.
Okay,
In the worst case scenario, everything is completely connected and there's a very small epsilon over here. So that's the worst case scenario. Like, the moment you zoom passes, everything is connected like here.
okay,
So over here we have a special epsilon over here, and that's what's going to give us our like nicely structured data set. So for this, since we're doing it for YouTube, I'll go ahead and explain all the details. I'll give it a little formal sort of explanation.
okay.
Yeah. Okay. Cool. So for persistent homology, we need some basics. Mainly what we need to do is we need to understand what we even mean by connection, right? We're saying, okay, sure, we have balls that increase in size. How do we exactly define this process? How do we define what happens when these two balls connect, right? So for that, I'm sure you've heard of a simplex probably while looking through this. Yeah.
Never heard of this in my life.
Really? Okay, cool. Then
maybe
I'll
maybe
explain this.
Maybe, but I don't remember.
Okay. So a simplex, right? It is a way to generalize a triangle. So in like intuitive sense, what we want to know is we want to generalize how to go about in triangles. So okay, if we have 3 points, the smallest do you say shape connecting all 3 points is a triangle. Or like this in more formal terms, if you have n points, then a simplex or an n simplex is the convex hull of the of endpoints. So I'll explain what this means. To understand things quicker, it's always best to look with examples. Okay, so let's take 3 points over here. Okay, so we want to understand what the three simplexes. And for the sake of this example, I want to show you that a three simplex is a triangle,
Okay.
right? So what do we mean by a convex hull? A convex hull basically means that if I have a set of points, right, and it has like this path between it, this path between it, and so on. So what it says is key the every path that I could possibly have lies within this triangle in some sense. So if I have to go to this point, then it what do you say? It lies within this triangle. It's better to show an example. I'll show you what is convex and what is concave
Yeah, I
in
know.
a
Yeah.
better explanation. Yeah. Uh, let's put a point over here, and let's put a point over here. So we've taken 5 points, and over here, taken 5 points. So visually, this obviously looks concave and convex, right?
Yeah.
How do we explain what it means to be concave or convex? So when I look at any two given points over here, the path that I draw between them lies within this region, yes?
Okay.
Similarly, let's just verify this for all points. So from this to this, yes, it lies in the region. This to this, yes, it lies in the region. This to this also lies in the region. And this to this also lies in the region. Yes?
Okay.
So if you can verify this for all of the points, then we say this is convex. Similarly, for this point, if we try to do the same, what do you say, the same verification,
Yeah, I see.
to verify between, say, I select this point and this path no longer lies inside this defined shape.
Okay.
Okay, so these are both hulls. Instead of a shape, we can say a hull. This is a concave hull, and this is a convex hull. All right.
Okay.
So when we, this is 5 points. Yeah. Now, uh, yeah. So the how is it defined? Yeah, right. So if we go back to our example now, not erasing it. There you go. Okay, cool. So if we go back to our example, yeah. So a three simplex is a triangle because yeah, if I draw the all points between them, any path between these points lies within the triangle. Similarly, oh, I'm sorry, my bad. This is a two simplex because it's 2D.
Okay.
It's not a three simplex. Similarly, a one simplex is a line between any two different points, and a zero simplex is just a dot.
Okay.
So a one simplex and a zero simplex. Right, makes sense so far, right?
Yeah.
So when we're generalizing in this direction, we're going from 0D to 1D to 2D. Now in 3D, we're going to have 4 points. How do we generalize these 4 points? 3D, I'm saying, three simplex. So in this point, what we get is a tetrahedron. Okay.
Yeah.
So similarly, you can verify that any point in, like, any path between these 2 points lies within the tetrahedron. And we cannot draw a 4 simplex because that is in 4D.
Okay.
Okay, so like that, you can just generalize. Yeah. Uh, so what we're doing essentially is when we're growing our balls, we're forming a simplex between them, right? So when two balls overlap, we get a one simplex. So like a 1D line connecting these two. When say all three of our balls overlap, then now we have to connect all three of these points, right? So we get a two simplex, which is our triangle. All right,
Okay.
makes sense.
Yeah.
Okay. Now a complex is not complicated.
Okay.
We're just taking a bunch of simplices together. So a set of simplices is called a complex. So mostly we'll be looking at what do you say, connected simplices. So for example, if I drew, let's just say, a triangle over here, I will draw a tetrahedron over here. What else should I draw? Another triangle over here and a line over here. Individually, these are all simplices.
Okay.
When I connect these two, when I connect all of them together, that's a complex. So individually, these are simplices. Now it is a simplicial complex because we're making it out of simplices.
Okay. 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 Okay.
Simplicial complex. Okay.
Yeah.
Now, yeah, these are all simplicial complexes, right? So I forgot what's the notation. Yeah, yeah, K. Okay. So this is generally we say K for our complex. Now, given a complex K, let's say K is a complex, filtration of a complex is the following. Of a complex. So basically, it is a way to sort of level up your complex. So given that you know your end product, let's say our complex is simple for this example, just an easy one, so that it's not too complicated. Okay, let's just keep this as our complex. So what we're going to do is, given this is our end product, we want something that leads up to this. So you could think of it as a subset of your simplicities, as a subset of your complex. So this is contained in this thing. This is contained in, say, this, and this is contained in just all these points. Okay, so yeah, just remember that over here I said set, right? So a filtration is basically just a sequence of subsets. So this is your first subset, second subset, third subset, and your final subset is the original complex. Okay.
Okay.
So in thinking of how, because I think both, like, you understand the general picture of persistent homology pretty well. Now you're growing balls to get your final
Yeah. Yeah. Yeah.
donut for this
And
case.
they
Yeah.
are connecting and
So
creating these different complexes as they are
yeah, so
connecting.
the process of
Yeah.
growing your balls is basically a systematic way of filtration.
Okay.
You understand?
Yeah. 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 I understand. I understand
So
what's up.
your balls are growing, right? Yeah, yeah, yeah. So every preceding thing, like, when epsilon is really small, all the way to epsilon is your perfect value, this is a filtration sequence. Yeah,
Yeah.
makes sense.
Yeah. Yeah. Yeah.
Okay, cool. So along with this, I'm explaining what persistent homology is. Also, I'm going to explain other generalizations that we can use. Okay,
Okay.
so some things are not, like, the things that are not explained are probably things that are just ideas that I've pitched. Okay,
Okay. But also,
so
I would like to know if you like, if you, how would you like figure out some patterns? What would you learn from data, from tokens, from bytes?
I'm not sure about that actually. I have no idea.
Okay. 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 Uh, okay. So just to
That's
keep.
something I guess we have to explore.
Okay, don't worry. I think just continue explaining with your dots, and we can convert bytes to dots. So then we'll figure out.
Yeah. Yeah, exactly. That's the thing. We have to figure out a way to take our bytes and put it, we can call it for fun as just a byte space.
Yeah. I think
But
bytes are numbers from 0 to 255. So we just group 2 by 2 like bytes, and then
yeah,
put them on coordinate
same thing.
system.
Basically, like,
Yeah.
okay, yeah. But then how do we make sense of, okay, so given a sentence, say, I thought a bus stop, something like that. So anything with like a repeating word, right?
Yeah.
So these are going to have the same tokens, right?
Yeah.
So how do we show that these things are repeating? Like, you're understanding? I was thinking, ki, okay, this has your tokenization here like that as some numbers. And I was thinking, ki, if this number and this number match, then we can sort of like, bend it over. So I was thinking maybe something like this.
Ah. Okay.
So this is the repeating thing. And this could be one way of giving structure. So our sentence continues like this, and it'll loop around and stuff like that as and when something is repeated.
Okay.
So that could be one way of it. But then the thing is, we wouldn't actually need to do persistent homology at all because it's already structured.
Okay. No
We
problem.
already
No
have
problem. No
our,
problem. You can just continue before I interrupted you about bytes. What were you gonna explain?
so I was just going to go in the formalism again.
Okay, that's good.
Constantly just need to be formal about it. Otherwise, if it's not defined with, then yeah, okay, good. Yeah. So yeah, so far we've defined what a simplicial complex is. Simplicial complex K. And we've defined its filtration. Okay. Now what we're going to talk about is algebraic invariance. So what exactly do we study about our data when it is unstructured? I had mentioned holes, right?
Yeah.
So if this whole thing, this whole thing, that's a pun. If this whole thing gives us a hole, then a hole is a type of algebraic invariance, is an algebraic algebraic invariance. Yeah. So what we're doing is we're finding a way to detect said holes or algebraic invariances. So formally, what happens is given what we call these are Betty numbers, right? So the number of holes a surface has is given by its Betty number, Bn. So Betty number 1 is going to tell you how many 1D holes you have. I think you can explain it as, just like something that's missing over here. Betty number 2 is going to tell you how many 2D holes you have. So if you have just a plain sheet of paper, your 2D hole is just a cutout.
Okay.
Similarly, Betty hole 3 is something like a donut. I like calling them donuts over toruses.
Yeah.
3D holes.
But
Cool.
shouldn't
So,
the 3D hole be completely? Ah, you mean inside of the donut? Donut is the hole. So I
uh,
thought the 3D hole.
right, I think I messed up the definitions a little. We should go to Wikipedia. Let's see. Wiki. Okay. Okay. So, corresponding to every Betty number, you have something called a homology group, HN, or a homology group. So yeah, these groups are basically gonna is another way of encoding what do you say? What number of holes you have in your given thing. So I think I'll explain that later if required, because this part of formalism is I'm gonna have to explain what homology is and what group theory is. Do you know either?
I know about group theory. I don't know how much knowledge you need, but I think if you want, you can just then skip this for now. Or
I'll skip this for now. We'll go like Yuki. Our generalization comes into a later part. So yeah, we can work on that later.
okay,
For now, I will go ahead and I will talk about my first, what do you say, idea that I have that I want to pitch. All right. So yeah, so the traditional way of applying persistent homology, or like you could say a pipeline, yeah. So you have your raw spatial data, right? And then you apply a filtration to it. Oh wait, and filtration, and you get a filtered simplicial complex, right? And then you apply homology to it, which is this thing over here, right?
yeah,
So homology, and you get something called its persistence modules. So this is where we're going to do our hole detecting and stuff. Okay.
okay,
And then after that, typically what we convert them into is barcodes, which is how we, do you say,
how we
determine how
sell,
long.
how we pay, how we sell,
Uh,
buy stuff in store.
yeah. Maybe you can get a discount with it.
Yeah,
Yeah. So, yeah, in typical, let me just scroll down. Yeah. In typical persistent homology, you are taking points and you're growing your balls around them, right?
yeah,
Of a radius epsilon, and you're going to keep increasing them until everything is connected. So I'll just, this a highlighter on. Yeah. So you're going to keep increasing them until everything is connected.
yeah,
So yeah. So everything is interconnected and you have a really big mess. Right.
yeah,
What my idea is that instead of now what you'll notice is every single ball. So suppose this point and oh wait, let me use a different. Yeah. This point and this point are really far, right? So for these two to be connected, the radius has to be at least this big. So every other point also has to have that really huge radius
Wait,
of
wait,
like
wait, wait,
this
wait.
large.
The radius needs to be half as big, half the distance between them.
Right, yeah, true. But what my point is, key, the radius of these points also increase when they don't need to increase further, right?
Oh yeah, yeah,
So beyond a certain point, like these points have connected as much as they should, but the points that are really far from each other still need to connect. So your value of epsilon is still going to go up. So what I was thinking is, what do you say? Instead of starting with all of our points with radius 0, let me erase. Let's see if I can erase this without making everything disappear.
okay.
Great. All right, cool.
Okay.
So, what my idea is that we start with a completely connected thing. Okay, this looks connected. This looks messy enough. So, for this to be connected to everything else, this needs, like, say this much distance from its furthest point. So, if I label all our points for just to make sense of this, let me go ahead and label everything. Okay. So 1, 2, 3, 4. This one is 5, 6, 7, 8, 9, and 10. Yeah. So I can give each of these points their own radius instead of having a single epsilon, instead of having one epsilon that goes for all of these things and increases the radius uniformly. I can instead have different sizes of epsilon that vary in their own speeds,
Okay.
is what I'm thinking. So instead of having an epsilon for all of these, I'm going to give each of these an epsilon 10 over here, epsilon 1, epsilon 2, epsilon 3, and so on. So I'm going to start with a fully connected thing. And instead of epsilon going from 0 to 1 and increasing in this direction, this time I want epsilon I for all different points to start at a distance that works for it, and I want it to decrease slowly. So epsilon I is going to be a unique number for each of these, right? Because this point is going to have a different distance for it to be connected to everything else. Similarly, this is going to have a different radius to connect to everything else as well. So if we scale this down, is what I'm thinking. Maybe we could do it faster, I guess, because now our points are not decreasing or increasing with the same radius. So in time t, this is going to be just this much smaller and stuff like that. I'm not sure how to code it yet, what we can see. So this is one potential idea. To look into. All right.
Okay.
And if we, what we can, funny name is we can call this resistant homology.
Resistant. Okay.
It's not an actual term. I'm just naming it that.
Okay.
Then another, yeah. So how exactly do I explain this? Yeah, I'm gonna need a new board. Just, okay. So yeah, going to talk about, which is the reason why I'm talking about this is because this is again another thing that we can possibly generalize. So next idea has to do with something called boundary homomorphisms. Boundary,
Okay. Okay.
boundary homomorphisms.
Okay.
So homomorphism, you can understand it as basically a map between some arbitrary group to another arbitrary group, or you anything algebraic to anything else algebraic. So it can even be vector spaces to vector spaces. So homomorphism is basically just a map,
Okay.
right? So we in persistent homology we have this thing called a boundary homomorphism, and it is defined as delta n. So what delta n is going to do, I'll explain with examples. Delta n is a linear map that basically spits out the number of n-dimensional poles. No, wait. That tells you that. That tells you that. Hmm. Yeah. So it's gonna take, say, you have again your, let's take our nice round looking diagram. So, okay, so basically what's happening here is we're translating everything, like I mentioned groups before, right? Homology groups.
Yeah.
So what we're doing is, in some sense, instead of, what do you say, having Betty numbers tell us, we're going to convert this in some sense into a matrix. And we're going to talk about homomorphisms between matrices, morphisms between matrices from one matrix to another. This homomorphism being delta n. So delta n is going to be the thing now instead, acting sort of in proxy of bn, beta n, betty n, is going to give you how connected everything is, which is sort of analogous to saying how many holes your surface has. Okay.
So you are making a proxy of Betty numbers.
In some sense, yeah.
Okay.
I'm not sure how to explain this.
Okay, but you can just continue. We'll figure it out later. Just continue.
That is mainly it. So I'll just explain how we define our delta n, right? So I'll start with some examples, okay?
Okay.
So let's look at what delta 1 is, right? So delta 1 is basically you're going to list out all your vertices. So let's take an example first. Okay, how many points is this? This is 6. Let's take one more. Okay, right? Then this. Okay, cool. So let's just shade this for aesthetics. Okay, cool. So if we label these now, yeah, great. Okay. So vertex 1, V1, V2, V3, V4, V5, V6, V7, right? Now we'll label our edges. So this is E1, E2, E3, E4. So E2 is this one, for just to be clear. E5, E6, E7, E8, and E9. Similarly, now we have to characterize our faces. Yeah, okay. So this thing is a face. So this is F1. A tetrahedron has how many faces? 3 faces, right? 4. Yeah, 4. So, and this front face is F2, F3. The bottom face, let's say, is F4. And this last face, will say, is F5. So I'll just draw it here. So this is 1. No, this is 2, 3, 4, and the back one is 5. Yeah, cool. Is it working? Yeah, there you go. Okay. Yeah, cool. Okay. So what we're going to do is we're going to list our vertices downwards now first. So V1, V2, V3, V4, V5. How many vertices do we have? 7 or 8? 1, 2, 3, 4, 5, 6, 7. Yeah, 7. 6 and V7. Right. And along our columns, we're going to list the edges. So E1, E2, E3, E4, E5. We have 9 edges, I think. E6, E7, E8, and E9. And let's just, oh wait, we can't get rid of it because we're kind of referring it. Uh, just move it then. Yeah, somewhat better. Let's move it here. Better, much better. Okay. So now I'm going to start filling these columns. So starting here, all the way up to here. Right? Now we're going to look at our diagram down here. And let's say we're looking at edge 1. So if vertex 1 and vertex 2 exist in edge 1, then I'm going to put 1 in the column for both of them. Otherwise, I'm going to put 0. So I'm going to look at the first vertex. Okay, the first vertex exists, so I'm going to put a 1 over here. Similarly, I'm going to go down, look at the second vertex exists, so I'm going to put 1 over here. Now I'm going to go down, I'm going to see vertex 3 is not connected. Okay, wait, I should probably use a highlighter. Vertex 3 is not connected with H1, so I'm going to put 0 here. Similarly, all of these are 0, 0, 0, 0. Okay.
Okay.
Now, with the next stage, I'm going to just go with one more row because this thing is tedious. So I'm not going to fill the whole thing. So now if we go for which edge, we do edge 2. So edge 2, let's just, okay, I can't erase. I will use purple. Yeah, so edge number 2, I'm going to look at vertex 2 and vertex 3. These are the only ones that exist. Vertex 1 does not exist in our thing. So vertex 1 is going to be 0. So vertex 1 is 0, vertex 2 is 1, vertex 3 is 1, and the rest of the column is 0 because the other vertices of V7, V6 and all don't lie. So similarly, we fill this whole matrix as such. We put in 0 if it exists, if it doesn't exist, and we put in 1 if it exists. Now, similarly, in the very same fashion, we have faces also in our diagram, yeah. So now delta 2 is going to be defined similarly. So instead, now you have V1, V2, V3 all the way down. Or was it edge? No, my bad. It was edge 1, edge 2. So edge 1, edge 2, edge 3, yada, 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 all the way. And then we have F1, F2, F3, and so on. And we fill this matrix. Similarly, referring, I think. And so basically, what I want you to notice is that over here, oh, where did it go down? Yeah. Okay, so we had the subscript 1 over here, right? This corresponds to a 1D simplex. So the 1 over here stands for this 1 over here. So along the columns, you'll notice all edges are basically lines, right? Lines are 1D simplexes. So we're seeing which, what do you say, zero-dimensional simplex, which is our dots or vertices, lie in our 1D simplex. So similarly, over here, we're looking for this 2 over here now corresponds to what? A 2D simplex. And now we have a face, not a face, now we have a triangle, and we're seeing which 1D simplices lie in our overall 2D simplex. Okay, so you're getting a feel for it, right? We'll have, so now if we go for delta n, what we're taking is we're taking an n simplex in our column like that, and we're going down a row of n minus 1 simplexes. And this matrix we're filling. And that's what corresponds to our delta n. Okay.
Okay.
So our my the generalization that I'm thinking of is that at any given moment we're seeing only an n simplex and an n minus 1 simplex, right? Doesn't make sense so far? Do you have any questions?
No.
Okay, cool, great. So my issue was sort of with this one over here. So I was thinking, key, okay, what if we had an n minus 1 simplex? Like how we had in, like, just when I was trying to define delta 2, you saw my confusion, right? I had f over here and I was confused if I had v over here or e,
Yeah.
right? So what I'm thinking is maybe there's some more information over here. So if we have an n simplex along our columns, what about an n minus 2 simplex? Furthermore, we can generalize it to, instead of just n minus 2, we can take it to, hey, how about all integers? So n minus d simplex.
Okay.
So this is the generalization that I'm thinking of taking it. So in that sense, we would define delta as a map with d and n over here. And it should be a matrix about n simplices and n minus d simplices. So I still have to check if this makes sense, because yeah, the matrix is like the matrix. Yeah, sure, I can make a matrix like that. I just need to see if I can actually do homology on this. So that's the part that I haven't yet thought out,
Okay.
because yeah. So that's basically all my thoughts on it. So yeah, one last thing is, we were when I was like, just going through my notes, right? I found something for our problem, but I'm not sure how to apply it. So uh, what is it? Yeah, we want to convert sequential data to spatial data. Yeah.
Yeah.
Um, what I've heard of is something called Mapper's algorithm. I'm not sure how to apply it in this sense though. Because see, what Mapper's algorithm does is it kind of works already on spatial data. I'm not sure how these papers have applied it to sequential data
But
or time series data.
um,
So
but we can
yeah, go
we
on.
can easily convert tokens or bytes into spatial data just by replacing it with some numbers each token or byte, and then grouping two and drawing on coordinate system.
Hmm. Yeah, okay, wait. So do you think you could like formally write that down? Like say given a byte, right? Given some byte, say, let's say a four.
From 0 to
Okay.
255, those are numbers from 0 to 255.
Okay. How many how many places are we looking at?
I
This
don't.
is four places. How many
Yeah, yeah,
places do we have?
yeah.
Five?
So 4 bytes, I guess.
Okay. So how do we map this into some coordinate x comma y?
You just take the first 2 bytes. Those are gonna be numbers between 0 and 255, both of them. So you take first
These
byte.
two, yeah.
Yeah, you take first byte to be x and second byte to be y.
But then you're losing all the information over here, no? So you're gonna have some words that map to the same coordinate because they start with the same number, right?
I guess if
So this is one, two, and this is like A, B, C. And suppose we had another one, one, two, D, E, F, something. Let's just say. So these two things would map to the exact same thing.
no, 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 no.
Exact
Uh,
same
no, no,
thing. So
no. I mean, we take every byte separate. So we take like next to
I
as
see.
well. Yeah.
Okay. So,
Every pair.
hmm. So, yeah, what is this? Okay. Is it working?
What?
Okay, there we go.
Okay.
Okay. Yeah. So what you're saying is we take them two at a time, like
Yeah,
this, and
yeah.
then like that, and then like that.
But we can
And
just
we have
we don't even need to
six.
stride like that. We can just take like these two and then these separate two and then these separate two. Which one do you think is better?
Yeah, okay. Yeah. These two first, and then some other pair
Yeah,
like that.
you go pair by pair.
So we have basically a set of all our pairs, right?
Yeah.
Oh, okay, I see. And then we do pH on this. And what's interesting, oh, okay, I have a kind of coolish idea.
Okay.
Okay, I will explain. I forgot, I think I haven't explained persistent diagrams. I got too, what do you say, uh, carried away by formalism. I will do that now. So I mentioned barcodes earlier. Yeah.
You mentioned what?
So
Ah, barcodes.
barcodes.
Okay.
Yeah. So persistent diagrams are the same thing as barcodes. So what we do is we have one graph over here, and what we call this graph is the birth death graph. Okay, so in this axis we have the birth. These are both in time. Okay, so a time t. So, and this is also death, again a time t. Okay, so what we do is there's this, yes. Okay, so when we're growing our balls, right?
Yeah.
It's lagging again.
I think it's
It's
okay.
working now. Yeah.
I think it's okay. I think it's okay.
Yeah. So we have our balls at an epsilon this. So epsilon is sort of increasing with time, na? So as time goes on, epsilon just increases. So as epsilon increases, we're basically going ahead in this diagram. So first, what we're going to do, okay, I'm going to need colors a lot in this one. Yeah. Okay. So what we're going to do is you'll probably see this a lot if you Google persistence homology. We're going to note the time at which some simplex is formed. Okay, so I will name two events. Okay, so there are two possible events that can happen in our graph. That is, first is birth, i.e., when some simplex, basically, when a simplex sigma, a k simplex sigma goes into a k plus 1 simplex. So, what I mean by this is that for any two vertices, this is a zero simplex, this is also a zero simplex, right? When they connect, and the zero simplex that was there before, it dies, and this births the birth of a one simplex. Now, as you add a third point over here and say these 2 points are now connected, so now this one simplex, and this one simplex, all of them die, and they together form a two simplex, which is this triangle.
Okay.
Okay. So this process of upgrading basically from a k simplex to a k plus one simplex, as we saw in our example, we started with one simplex and we went to a two simplex, right?
Yeah.
This is birth. Okay, depth is basically what do you say? Whenever what do you say? We want to see how long once our simplex is formed. So say, is it drawing now? Yeah. Say this line is formed, right? And this line is formed. We want to see how long these lines actually survive before they upgrade into, say, this line
Yeah, the next one.
and form a two simplex. So, do you say the time that elapsed between the formation of this thing and the death? Basically, death meaning it just converts into some other simplex.
Yeah.
So that is called do you say is going to be shown over here. So first we're going to have all of our points coming into just basically forming. So these are all zero simplices. So basically they just instantly formed. Okay, that basically you'll see in these diagrams that they just instantly just uh, there's just a line of what do you say, you could see blue. Let me see if I can present it.
So
Versus, I'll
I
just
uh,
type
I
in.
understand they all get born at the same time in the beginning of this X birth axis.
Yes, exactly. I'll bring in this example for the video.
Okay.
Oh yeah, I can't. Yeah, is it not? Cool. So over here, let's use right. This is basically all our points loading in, right?
Yeah.
And as our epsilon increases, these are basically the formation of our higher dimensional simplices. So over here, orange is about H1, right? And H1 corresponds to our one simplex. So basically, what this is saying is these are the time of like depth and formation of our lines, 1D lines. Similarly, the green ones over here, they correspond to H2. So this corresponds to our phases. Now, what we're interested in is okay, we're constantly getting like red, green, not red, green, we're getting orange, green, etc., and so on, right? How do we actually figure out which of these features are living for the longest, right? So that is characterized by its distance from this middle line. The reason why you can't have anything on the other side of this line is because you can't really die before you're born, right?
Yeah. Yeah.
So uh, that's why there's no point that exists on this side.
Yeah.
And that's why all these points lie on this side. But the further this point is from what do you say, diagonal line,
Diagonal. Yeah.
is telling us how much time this thing was alive for.
Yeah.
Or in another sense, this tells you the persistence of that feature. So somewhere in this, let's erase everything so that we can actually see what is the. Yeah. So if we remove everything, we can see that the longest staying feature is this one over here.
Yeah.
So this, at this point of t, that's the structure we're interested in. So hopefully in this structure, or like just by guessing, this is going to be something that looks nice, sort of like this. Just like, just for example's sake. So this is going to be something that looks nice, that has a very clear hole. Everything looks nice and neat. Nothing is over connected. All the close points are the ones that are connected, while all the far points are still disconnected. So this is our special thing, right? This
Okay.
is our special point.
Okay.
So at this time t is what we're interested in. Say this is 0.5. Okay. So what we do is, say you have, okay, so for any given structure of data, you're going to have its corresponding persistence diagram, right?
Yeah.
Now, what they do to relate how close any two data sets are. So this data set, and say I have this data set, or actually insert that instead of saying a new one. Let me just say, okay, yeah, so I have this data set, right? And I want to see how close this thing is to this nice one that I have here. Okay, so take any two different data points, just get rid of this line over here. Take any two data sets over here, data set 1 and data set 2. Set 2. So how do I relate how close they are to each other? What I do is I take this data set's persistence diagram. So just draw something like this, and I take this diagram's persistence uh, diagram, and I relate them by something called, I almost never remember how to spell his name. Wasserstein distance.
Okay.
So the Wasserstein's distance is basically was initially defined to talk about how two different distributions are, two given probability distributions are. So if these two distributions look very similar to each other, according to the Wasserstein distance, you could say they are close.
Okay.
Otherwise, say you had to relate this thing to a distribution that's uniform. So just a block like that. The Wasserstein distance will tell you it is far. Okay.
Okay.
So similarly, instead of having distributions in this case, we have persistence diagram 1 and we have persistence diagram 2.
Okay.
And the Wasserstein distance is going to take these two things and it's going to tell you it's either close or it's far. Okay, and that definition I'm not sure how to use, so we will have to work that out.
Okay. Okay. That's
But
okay.
these are all, yeah, these are all known things. So we just have to pick a decent paper and we just have to cut, copy, paste everything. There's not much to originally come up with. Okay, so that's the final part, persistence diagrams. And yeah, what do you feel? Does this all make sense?
Yeah, I understand everything.
That's great. That's actually really great. That's awesome.
Also,
Okay.
I read before a little bit.
So
I knew before a little bit about this persistent diagram as well. So, and
yeah, that's great then.
I didn't know about the Wasserstein's distance, but now I know.
Yeah, so yeah, Wasserstein distance are for distributions. They're very useful in, like, I'm familiar, I'm not familiar, I would say, but I've seen them in probability distributions a lot. So like in diffusion models, when they are like, I don't remember, but they were teaching a couple of theorems and stuff like that, and I was like,
Ah,
that was where I came across it
yeah,
most
yeah, yeah,
frequently.
yeah. It makes sense. Probability distribution in diffusion models. Yeah.
Yeah, yeah, yeah. Cool. So that's it. That's all I have for now.
Okay. Thank you. I'm gonna post this on YouTube. You can say thank you for watching and see you in the next video.
Yeah, I'll say that. So thank you for watching, and I'll see you in the next video.